Alright, we are back in section 10.3, comparing two independent population proportions. So we're looking at, again, two samples, but we're looking at proportions this time rather than means like we were in the first section. So suppose that a simple random sample of size n1 is taken from a population where we can define p1 hat to be the sample proportion for that first sample, and that we get from x1 over n1, where x1 is the individuals with our characteristic, and n1 is our sample size. And then similarly for the second sample, we have p2 hat, which is x2 over n2. These are approximately normal, with a mean value of p1 minus p2, and standard deviation given right there. Okay. And then provided that we have sufficiently large sample sizes, we can write the standard version of our z-score, or our test statistic. So let's look down in the note here. This is going to be a little more useful for us, because we're going to be using what's called a pooled estimate of p. So in this case, that's where we have p hat. So not p1 hat or p2 hat, but just p hat, which utilizes the data from both the first sample and the second sample in it. Okay, so it uses first and second sample. That's why we call it pooled, because we're pooling both data sets together. And the test statistic for comparing two population proportions is right here. So it's going to be, if we're looking at this one right here, p1 hat minus p2 hat over the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2, which I know is a complicated looking formula, but it's just a matter of plugging the right things in the right places. Okay. So when we're testing two proportions from independent samples, of course they do need to be independent, and then we oftentimes need to check this condition, make sure that they are sufficiently large in order for us to be able to work with them. Otherwise, the data that we get might not be accurate. Okay. Our process, very similar to what we've seen before. So determine the hypotheses, determine the type of test, select a significance level, compute the p-value, compare it with alpha, and then make a conclusion. Okay, so it's exactly the same as the ones with the sample means, just now working with the proportion instead. Okay, so let's look at a couple examples. So an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. The economist obtains a random sample of 800 urban households and finds that 338 of them have internet access. The economist obtains a random sample of 750 rural households and finds that 292 of them have internet access. Test the economist's claim at the alpha equals 0.05 level of significance. So first off, as always, our hypotheses. So H0 and H1. So our null is always that they're equal. So P1 equals P2. And then the alternative, he believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. So that the first one is greater than the second. All right. So we need a few pieces of information here, but first let's just verify quickly that we can work with this. I'm going to do it on a separate sheet just because with my stylus I have to write a little bit bigger, but you can just do it in the same space right here. But let me go to a blank page to do this. Okay. So let's verify. So verify we can test. Okay, and we do that by taking n1 p1 hat times 1 minus p1 hat and we take n2 p2 hat times 1 minus p2 hat. Okay, we would get those values, so let me go back and let's find those values. Okay, so p1 hat, from our first sample, we saw that we had 800 urban households and 338 of them had internet. So that's 338 out of the 800, which is approximately 0.4225. And P2 hat, that is, we have a random sample of 750 rural households, and 292 of them have internet. So 292 out of 750, which is approximately 0.3893. Okay, so we got P1 hat, P2 hat. So let's just run those down over there. Okay, so this is going to be N1, our first sample size, that's 800. Oops. 800 times P hat is 0.4225 times 1 minus P hat, P1 hat I should say, is 0.5775. This value is approximately 195, which is certainly greater than or equal to 10. So our first sample size is sufficient to run the test. And then the second one, our sample size was 750. Our P2 hat value is 0.3893. So 1 minus P2 hat is 0.6107. This is approximately 178, which is certainly also greater than or equal to 10. So it gets a big check from us that we are able to run a test on this, so that we do have sufficiently large sample sizes here that we can work with appropriately. Okay, so let's go back. Hopefully you just stayed right there. Okay, so we have those two values. We also are going to need to get the pooled estimate. So that's going to be just P hat. I'll do this down here. So just P hat. So that's going to be x1 plus x2 over n1 plus n2. So that's 338 in the urban plus 292 in the rural over 800 urban plus 750 rural. Run that computation. That's approximately 0.40645. That's what we get for our pooled estimate of P. And all of this has been building up to finding that test statistic. Okay, so our test statistic, Z0, that's going to be P1 hat minus P2 hat, so that's 0.4225 minus 0.3893 all over square root of P hat times 1 minus P hat, so that's going to be our pooled estimate, so that's 0.40645 times 1 minus that number is 0.59, I can't make a 9, 59355. So you can see these take up a bit of space here, times square root of 1 over the first sample size, so 1 over 800, plus 1 over the second sample size, so 1 over 750. Okay, so run that whole computation through Desmos or calculator, and we get 1.3299. Okay, 1.3299. So that's going to be our test statistic in this case. Okay, so let's go ahead and find our p-value. So that's the probability. Again, this is a right-tailed test, again, because we have this greater than over here. So we have p-value probability that z is greater than 1.3299. And that is, if we use our z-score, not the t distribution, we don't need degrees of freedom here, this is just the z-score, that's approximately equal to 0.09178. Okay, and compare this to alpha, which we established in the problem was 0.05, and 0.09 is certainly bigger than 0.05. Right there. So since the p-value is bigger, this says that we cannot reject the null. So we say do not reject the null hypothesis. Okay, so a lot of not rejecting in these sections so far. So what does this tell us? Well, it just means we do not have sufficient evidence to make the conclusion they want to make. So they believe that urban households have greater internet access proportionally than rural households, but we don't have enough evidence to support that. Okay, so we can go ahead and just say there is not sufficient evidence to conclude that urban households have greater internet access than rural households. Okay, so we just don't have sufficient evidence to make that conclusion, okay, at least with this data set. All right, then let's look at one more example here. So on a decidedly darker note than internet access, so a concerned group of citizens wanted to know if the proportion of forcible rapes in Texas was different in 2011 than in 2010. The research showed that of the 113,231 violent crimes in Texas in 2010, 7,622 of them were forcible rapes. In 2011, 7,439 of the 104,873 violent crimes were in the forcible rape category. The groups claimed that the proportion of forcible rapes was different at a 2% significance level. Okay, so a lot of numbers going around right now, but first things first, we should create that hypothesis. So the null hypothesis alternative. Always a good place to start on these tests. If you're not sure where to go, just make hypotheses. So we know that the null hypothesis says that these proportions would be equal, and this group is trying to conclude that the proportion of forcible rapes was different at the 2% significance level. Keyword here is different. So we're not saying greater than, we're not saying less than, we're just saying different. So they're concluding that P1 is just not equal to P2. All right. So, and then of course our alpha value in this one, a little bit different, but it's our 0.02 significance level. So let's get the pieces we need. So P1 hat. So P1 hat, that's going to be 7622 over 113,231, which is approximately 0.0673. and P2 hat. That's going to be 7439 over 104,873, which is approximately 0.0709. And so you can see that I chose my P1 to be the 2010 data and P2 to be from the 2011 data. If you switched those, it's not going to make a difference. So the z-score you'll get, I'll explain why it's not going to make a difference in just a minute, but it doesn't matter which one you picked. So it would work out the same either way. And then our pooled estimate, so P hat, that's 7622 plus 7439 over these huge numbers, so 113,231 plus 104,873. So our p hat value is approximately 0.06905. Okay, so it's hovering between those two, which makes sense, right? Because it's a combination of those two, so it's between them. Okay, so this is kind of all of our data to start us off here. Then we have our test statistic, Z0. So we do P1 hat, 0.0673, minus P2 hat, 0.0709, over square root of P hat times 1 minus P hat, so 0.06905, times 0.93095, times square root of 1 over 113,231 plus 1 over 104,873. Okay. Which in this case, because we see the proportion for 2011 is greater than that of 2010, we're going to be getting a negative number here because the numerator is going to give us a negative, or it's smaller minus bigger number. So this, if we run the computation, is negative 3.313 approximately. Okay. Now, if you had done this the other way, and you had decided to make P1 based on 2011 and P2 based on 2010, that's fine, that's okay. You would just get positive 3.313. The reason this isn't going to matter is because this test is a two-tailed test. And if you're wondering why, just go back and look at the alternative hypothesis. So the alternative hypothesis said that P1 is not equal to P2 right up here. So that means that it could be on either side, right? Greater than or less than. So here we have our normal curve, and we're going to have our two test statistics. That's going to be negative 3.313 and positive 3.313. How do we know they're the same? Because of symmetry. So in these types of tests, we have a normal curve. Normal curves are symmetric. Okay, so our p-value is going to be a combination of both of those areas. Okay, so for our p-value, we could compute the areas separately and just add them, but we know that actually this area here is going to be the same as this area here. So all we need to do is find one of them and double it. So we're going to just take 2 times the probability that z is less than negative 3.313. Okay, or alternatively, you could have done 2 times the probability that z is greater than positive 3.313. You could have done that one instead, and it would give you the same thing, okay, exactly the same area. Okay, so we run that again using our z-score, And this is going to give us approximately 0. Even after multiplying by 2, 0.00092. And if we look at that p-value, that p-value is certainly smaller than our alpha value, right? So p-value is less than alpha, which was 0.02, which means for the first time today, we do get to reject the null hypothesis. Okay, because our p-value is finally smaller than alpha. So we can say that there is sufficient evidence to show that the proportion of forcible rapes was different between the two. Not necessarily saying greater than or less than. We're not making that conclusion. We're just saying that it was different. So not the same, okay, not equal. So we can say there is sufficient evidence to conclude that the proportion of forcible rapes was different between the 2 years. All right, so that's our conclusion that we're going to be able to make. And that's the end of 10.3. So you'll see 10.4 down here, the matched pair samples. We're not going to be doing this one. This one focuses more on dependence, and that's not really where we're primarily going to be focusing in this class. So we're going to skip over 10.4 and just stop at section 10.3 so we can stop at the independent samples. So, so that's it for